All right, let's look at the implicit differentiation. All right, the derivatives we have been taking started out from always y equals some function of x. Then we take the derivative, say y prime is equal to f prime of x. All right, so this is called explicit differentiation because you start out from explicit formula for the function, then you take the derivative from there. Right? But the implicit differentiation allows us to take the derivative directly from my equation like this, which is not in the form of y equals something. Right? So in order to be able to take the implicit differentiation, we have to be able to distinguish these two derivatives. Right? So look at the first one. Right? So this is a derivative of y cubed with respect to y. And y is a function, some function of x, g of x, right? So when you have a matching, say here, variable here, its a function is written in terms of y, then you're taking a derivative with respect to the same variable. Then this is just a regular derivative. So derivative y cubed with respect to y is just a power rule. Put 3 in front, keep the y, and subtract 1 from the power. So 3y squared is the derivative of y cubed with respect to y. How about the second one? So it's the same function, y cubed, but we are taking a derivative with respect to x instead. All right? So how do we do that? Right? Maybe we'll look at it this way. So since y is a function of x, so I'm going to rewrite it as, I'm going to just replace y with the g of x. So it's going to be a g of x, and so cubed. Right? So we want to take the derivative of this guy with respect to x. So this is the general power rule. So you have 3 in front. Keep the same quantity, g of x, inside. Subtract 1 from the power. Then you have to multiply by derivative of the inside. Right? So that's the derivative there. So if you go back to the regular notation, right? So 3 is 3. Right? Remember, g of x is just the same thing as y. So it's y. And squared. So you put squared. Right? Now we have g prime of x, which is just a derivative of y. So we have to multiply by derivative of y. So I'm going to write it as a dy over dx. Right? So notice the difference. So if you're taking a derivative with respect to the same variable, it's going to be just only 3y squared. Right? But if you are taking a derivatives of something that's written in terms of y with respect to x, so they do not match, then we get same thing, 3y squared, but you have to multiply by dy over dx. All right, so this is this is coming from the chain rule. All right, so let's look at this example. All right. We want to take the derivative of this equation right here. Then try to find dy over dx. Right? So we're going to take the derivative of both sides with respect to x. So derivative with respect to x of the left hand side is e to the y. Alright? Then we're going to take the derivative with respect to x of the right hand side, which is x squared plus y squared. Right? So let's do that. Alright, so when you take the derivative with respect to x, but this is written in y, so what you do is just go ahead and take the derivative in a regular way. So it's going to be exponential function, so it's going to be e to the y. Alright, but since these variables are different, you have to multiply by dy over dx. Right? Right, so let's take a derivative of x squared with respect to x. So in this case, variables match, so it's a regular derivative. So derivative of x squared would be 2x, right? Plus. All right, now we take the derivative of y squared with respect to x. So this is going to be 2y, but you have to multiply by, since these variables are different, we have to multiply by dy over dx. All right, so that's how we take the derivative of both sides with respect to x. Then what we are looking for is actually dy over dx. So we are looking for dy over dx, which shows up here, and another one shows up here, right? So we just have to solve for it, right? So first thing we do is I'm gonna put all the terms that has dy over dx on the left hand side, right? So what we need to do first is I'm gonna have to move this term right here over to the other side, right? We can do that by subtracting 2y and dy over dx, right? So we're gonna get so you have e to the y, all right, dy over dx was already there. Then we have to subtract 2y dy over dx, right? Then right hand side is going to be just a 2x, right? So since dy over dx is in common, we can factor it out. So I need room, so I'm going to go up here, right? So this is going to give you, right, by factoring out the dy over dx, we'll get, right, so you have a e to the y from there. All right, maybe I should circle that. So we took care of this guy, so we factor this guy out. All right, then we took care of e to the y from the first term. All right, then you have negative 2y there. So we're going to put minus 2y here. Right? Then this is equal to 2x. All right? So we can find the isolate dy over dx simply by dividing through by quantity e to the y minus 2y. All right? So dy over dx is equal to 2x on top e to the y minus 2y. Right? So that's the expression for dy over dx, which is the derivative of y with respect to x. Right, and part B of this question says that we want to evaluate this derivative at x equals 1 and y equals 0. Right, so it's easy enough. We can just plug it in. Right, this is going to be equal to, right, so x is 1. So this is the x value. So right here, so this is the x value, and 0 is the y value. All right, so it's a 2 times plugging x is 1, right, e to the, right, y is 0 minus 2 times 0, right? So this is going to be, right, so 2 on top, then you have e to the 0 is 1 minus 0, so it's 1. So answer is 2, right? So we can find the derivative using implicit differentiation. You just have to take the derivative, carefully, then solve for dy over dx. And we can also evaluate the derivative at the specific point. In this case, x equals 1 and y equals 0. but all you have to do is plug in these values, right? That's it. I hope that this was clear.